Welcome back once again. Hopefully this will be our last video for this topic on beam deflections, and I plan to do two more sample problems, and the goal is that so that we can develop our skills regarding this beam deflections using the method of superposition. Okay, so let's get started. Now, this problem is taken from the textbook by Beer and Johnston, and right here it says determine the slope and deflection at D for the beam and loading shown, knowing that the flexural rigidity of the beam is EI is equal to 100 meganewton meter squared. So here's our beam conditions. It's a simply supported beams, and we have a uniformly distributed loads plus another concentrated loads acting at this point, and the point here is the point D. So here's our A, here's our point B, and here's our point D. Now the distance from this beam support from point A to D is 2 meters, and the total length is 8 meters. Okay, so the first step that we do usually is to separate the loads, and that is to separate first. Let's say right here we have a simply supported beam but only concentrated loads, and right here we have this simply supported beams but only under this uniformly distributed loadings. Okay, so we need to evaluate the deflections right here. Okay, so to start, then let's analyze this. Let's call this beam 1, and this is our beam 2. Okay, so the next step is to solve for the deflection and slope produced by the concentrated loads. Okay, and from the table, this is actually case 7, so just like the same as our previous sample problem. So this is case 7, and the condition is that we have a condition of what else? I think this 0 less than x less than a. Okay, so here it is. Okay, so here it is. Here's our beam condition. This is case 7, and this is our expression. So let's just copy this. But I think let's just label first all the symbols. I mean, if for P this is 150 kN. B, the distance B is 6 meters, right? So 6 meters, and the distance A is 2 meters. A is 2 meters, and L, okay, L is 8 meters. Okay, so the equation is let me just copy it, bx all over 6 LEI times L squared minus x squared minus b squared. Okay, so what I'm going to do right here is just to substitute all the values of the given right here, and what will be the resulting expression is just simply the deflection as a function of x. Okay, so let me do that. This is 150, right, kN, but I have to convert this to n, to just newtons. I mean, all the units should be newtons and meters. But this will be 150 times 10 to the 3 times the distance b, which is 6, right, all over, okay, 6, okay, times 8 times EI of 100 times 10 to the 6. Because this one is given 100 meganewtons, so that's times 10 to the 6. Okay, and we have x right here. That's the unknown, or that's the variable x. Okay, times this L squared. L squared is 8 squared minus x squared minus 6 squared. Okay, so you see here that the deflection is just simply a function of x. Okay, and if you simplify the values of the numbers, this is just 16 times 10 to the 3, and this is x, and this term right here, this is 28 minus x squared. Okay, so we are asked to find the deflection, actually deflection and slope. Okay, so how do we determine the slope if it's not in the table? Because right here we only have slope, but at this point, slope at A and slope at B, and we are asked to find the slope somewhere in between. So just recall that the slope is just simply the first derivative of the deflection with respect to x, and if we do that, our expression would be 3 over, actually this is just a product rule, so you can just include this or just these two terms right here. Okay, 16 times actually 16 times 10 to the 3 times x, right? Or let me simplify. I think we can just use this. Let's just take this out from the derivative operator. 16 times 10 to the 3, and here's our product rule of this. So x times the derivative of this second term, this is 28, oh sorry, this will be 0. Okay, minus the derivative of x squared, this is 2x, right? Okay, plus this term, plus 28 minus x squared times the derivative of this x, which is just 1. Okay, so that's our or let me simplify. Times 10 to the 3, and this is x minus 2x, so that's gonna be minus 2x squared. Okay, plus what is this, 28 minus x squared, so this will be 3 all over 16 times 10 to the 3. What else? Minus 2 minus 1, so this will be minus 3x squared plus 28. Alright, so let me box this. This is our equation for the slope, and this will be our equation for the derivative. Okay, and we want to evaluate this x at x, I mean the deflection at x is equal to 2, because that's where that's where we want to find the deflection. Okay, so let's write here at x is equal to 2, and if we substitute all the values, what we get here is the delta. The delta is just equal to 9 mm, and the theta, the rotation, is just equal to 3 over 1000 radians. Okay, this is in radians, or in terms of degrees, or let's just put it this way, 3 times 10 to the 3, actually negative 3. Okay, and this is radians. Okay, sorry, this is our theta 1, and here's our answer. Okay, so the next step is we just have to do it the same way for this beam loading conditions. Okay, so the next step is to solve for the deflection and rotation produced by the distributed loadings. Okay, and right here, this will be, so if this is case 7, this will be case number 8, and we only have one expression for the deflection. Okay, so This is case 8, and the deflection equation is just this one, 24 EI times L squared minus 2LX squared plus X cubed. Okay, and the parameters are this distributed loadings. This is 20 kN per meter, and our EI is 100 meganewton meter squared, and the length is just 8 meters. Okay, so if we substitute all these values of these parameters to these equations, what we get is it's this expression, 1 all over 120 times 10 to the 3, right? That's our x. I mean the first term times x, right? Times this 512 minus 16x squared plus x cubed. Okay, and if we take the first derivative of this deflection, what we get is the slope, which is just, okay, so let's factor this out. I mean, let's not include this in the derivative since this is just a constant. So 120 times 10 raised to 3, and the derivative of this product of these terms. So first is x times the derivative of this of these terms. So this is just 0 minus 16. This is just 16 times 2, okay, will be minus 32x, right, plus 3x squared, right, plus this one times the derivative of this. So plus 512 minus 16 x squared plus x cubed. Okay, so that's gonna be our expression, and we can actually simplify this if we want, but let's just leave it like that. Okay, so let's evaluate now. At x is equal to 2, the deflection is actually, if you substitute x is equal to 2 to this deflection equations, what we get is a deflection of 7.6 mm. So take note, I converted the units to mm. Although we started with meters, we converted it to mm. And the slope is equal to 0.00293. So for the slope, you just have to substitute the x value in this expression. Okay, and therefore, right, let's write here, therefore the deflection at D is okay, the deflection produced by the concentrated load plus the deflection produced by the concentrated load, which is just 9 plus 7.6, this is 16.6 mm. Okay, and for the slope, which is just simply the same slope produced by the concentrated load plus the slope produced by the distributed loads, and this is just 3 times 10 to the negative 3 plus 0.00293 is equal to 5.93 times 10 to the negative 3. This is in radians. Okay, so that's how we did it. Okay, the next one is, let's solve another problem, and this one needs a little bit of manipulations because we don't have these loading conditions in our table. Okay, so this is our last problem. This is taken from the textbook, in this textbook, and here it is. Here's the beam conditions. This is simply supported beams, but the distributed loadings is somewhere in between. So it's not one side of this is not connected, or is not touching this end support right here. Okay, and we don't have that in the table, because if you check right here, we only have this concentrated loads at the midspan, concentrated loads as not at the midspan. We have a concentrated load all throughout the beam length, and right here we have a distributed loads, but you notice that this is just a portion, and the one end of the distributed loadings is touching this pin support or this end support. Okay, so we don't have like this one. Okay, so we don't have this condition, so we need to have manipulations in the loadings. Okay, so for this solution, the first step is to actually separate the loadings, but we don't have anything to separate here, but rather we'll use the term manipulate, right? Manipulate the loadings to fit the available beam conditions in the table. Okay, so how do we manipulate that? Is by this. So if this is our first beam, we only have this, right? We only have this. So let's extend one of the loadings to one end. So something like this. So here's our pin support, and here's our roller support, right? And this is 600. This one is 600 Newton per meter. Now let's label the distance. This one to this end, this is actually, we have 2 meters. 2 meters, and from this point to this end support, you will notice we have 3 plus 1, so that's gonna be 4 meters, and the total of this is 6 meters. Okay, so which is A? Is it this 2 meters or the 4 meters? So going back to this table, you will see that the distance A must be the distance corresponding to the portion where there is a distributed loadings. And the letter B is the portion where there is no loadings. Okay, so this will be A, and this will be our B. Okay, but this one, you would notice we extended it here, but it's not going to be the same as this one, right? Because right here it's only up to 3 meters. So therefore we need to subtract this portion right here. Okay, and we can do that by using another beam. However, the loading will be upward. Actually, we should have drawn it in the opposite side, like this. And so let's not include this. Let's not include this. Should be these loadings, right? So this one is still the same magnitude, 600 Newton per meter. Okay, so again, sorry about this erasures, but the point right here, I just flip this out, but it's just actually the same idea, I guess. Okay, and the distance right here, here's our distance, right? This is our A distance. This is 1 meter. Okay, this is 1 meter, and the B distance, this will be 5 meters. Okay, so here's our beam 1, and here's our beam number 2. So the next step is to solve for the deflection produced from beam 1. Okay, so from beam 1, this is actually both of the beam will have case 9. Okay, so case 9, and by the way, we also need to draw the deflected shape. So right here probably it's gonna be something like this, and this one will be probably something like this. And we are asked to find the deflection at the midpoint, so it's right here. It's the deflection at this point and right here. Okay, so this one, the deflection is within the portion where there is distributed loadings, and in this beam number 2, the deflection is not, or I mean the deflection is in the portion where there is no loadings. Okay, so therefore, if we select from the tables this beam 1, this is case 9, and we have the condition, this condition A, and we substitute and we select the expression for the deflection. This is 24 EI times x, right, times A squared times A minus 2L squared plus 2A plus LX cubed. Okay, so here's our expression, right? And our parameters, our A is 4 meters, our B is 2 meters, our L is 6 meters, and our distributed loadings is 600 Newton per meter. Okay, so if we substitute, actually we are only asked to solve for the midspan displacement, so we don't need to solve for the slope. Okay, so if we substitute all this, that's right here, if we substitute all this to the given expression, we have this one, EI times this deflection is equal to 25/6x times 64x squared plus 6x cubed. Okay, and therefore at x is equal to 3, EI times the deflection is equal to 7,625 Newton per meter cube. Right? So that's it. Then we also need to solve for the deflection produced from beam number 2, and this is still case 9, but this is A is less than or equal to x, is less than or equal to L. The expression is times L, sorry, there should be L right here, 24L times EI, and this is minus L plus x, right, A squared minus 4LX plus 2x squared. Okay, and our A is, okay, so here's our A. Again, the A should be the loaded portion, and this is 1 meter. And our B, actually we don't need the B because there's no B right here. So let's just write the L, is 6 meters, and the distributed loadings is 600 newton meter, actually newton per meter. Okay, so once you have that, substituting all the values of the parameters, we get this expression. Sorry, we get this expression. It's equal to 25 all over 6 minus 6 plus x times 1 minus 24x plus 2x squared. Okay, and therefore at x is equal to 3, our EI times the deflection is equal to 662.5 newton per meter. What's the unit of this? I think newton per meter cube. All right, so that's it. And finally, we have to the total displacement at midspan is, okay, so EI times the deflection at x is equal to 3 is equal to EI times the deflection produced by 1 plus EI times the deflection produced by 2 by the second beam. Okay, and therefore this is just 7625 minus 662. Okay, so why is it minus? It's simply because the deflection produced by this is downward, whereas this one, the deflection produced by this is upward. Okay, so they have different directions, and therefore you need to do actually this is algebraic sum. So when you say algebraic sum, we also need to take into account the direction. Okay, and this is EI. Of course, there should be EI here, and there's going to be EI right here. This is equal to 6,960 newton meter cube, and the direction is downward. Okay, so in summary, let's review what we did. So if we don't have a if the given problem is it doesn't have or it doesn't fit, or there's no available beam conditions from the tables, then what we can do is to do manipulations. Okay, and so that's why the first step that we did is to manipulate. What we did is to extend this loading to this roller support, and then we just have to minus that. Okay, so extend that, and then another beam will be the opposite direction. Okay, so right here, and the distance is just 1 meter. Okay, and again, just take note, the A should be the distance where there is loadings, and the B is the unloaded portion. Okay, so we substitute all that, and then we went to the table, and we found the appropriate select appropriate cases, and then we can obtain these deflection expressions, and we substitute all the parameters, and we can get the values. So we do that for beam 1 and beam 2, and then finally we just have to add them up. Okay, so that's the method of superposition. Okay, so that's all. In our next video, we'll be discussing our next topic, which is statically indeterminate beams. So we'll also use method of superpositions for solving indeterminate beams. When I say indeterminate beams, we have support conditions or the support reactions are greater than the available equilibrium equations. Okay, so we'll do that. We'll use this method of superposition, and also another method, since there are actually a lot of methods for solving statically indeterminate beams. So we'll only consider method of superpositions and I think the moment distribution method. Okay, so that's all. Thanks.